When we hear geology, our minds are taken back to eons ago when great mountains formed, huge canyons were eroded, and giant volcanoes erupted, all creating spectacular landscapes that amaze us. There is an old saying that you can't judge a book by its cover, and the Gulf Coast is a great example of this wisdom.
Hello, I'm Myron Cook. I've had the good fortune of working the geology of the Gulf Coast extending out into the Gulf of Mexico. And let me tell you, it's absolutely astounding. It's too bad that millions of people drive over or boat over this amazing geology unaware. Furthermore, this region provides a great opportunity to flip geology. I know you're probably wondering what I mean by flipping geology. Well, when we think of geology, we're normally thinking of distant time in the past, aren't we? But it turns out using basic geologic principles, you can gain great insights into the future. I'm looking forward to discussing with you both the past and the future of this region.
Let's start this journey by going to the Great Taklamakan Desert of China to see the world's largest alluvial fan. In fact, in this area there are two of them the same size. This beast is 36 miles across. Alluvial fans form when an intermittent river going down a steep slope encounters a relatively flat basin floor. The deposition typically occurs during flooding events, with the channel or channels migrating through time back and forth, creating the fan shape. Zooming in on this satellite image of a nearby fan, we see how the channels branch out down the slope. They are called distributary channels. It turns out that similar processes occur in the ocean deep underwater, and the fans can be much, much bigger. The Mississippi Submarine Fan of the Gulf of Mexico is a case in point. It was known for some time that there is a fan-shaped deposit in this region, and in 1987 the government completed a program of collecting a special type of high-frequency sonar known as side-scan sonar. This technology reveals details within the sediment up to a few meters deep. And here is the image created from that survey. Let's look a little closer. This really is a spectacular image. The lines that we see, the diagonal lines cutting across the image, those are artifacts from the acquisition. The average water depth out here is an amazing 10,000 feet. The more you look, the more you see in this image. Lots of distributary channels scattered throughout, also a main channel that runs right down through this area. Looking closely, one sees that there are three large fans that make up a fan complex. And is this gigantic? Let's look at it relative to the size of the alluvial fan we looked at. I've inserted an image of the world's largest alluvial fan here. Wow, it sure looks small, doesn't it? In fact, the Mississippi Submarine Fan along the width of this line is about 220 miles. The main channel of this fan points at this canyon. Let's take a closer look. This is quite a canyon. It's about 15 miles wide and 1,500 feet deep. It formed when sea levels were about 400 feet lower than today. During the sea level lows, the shelf was exposed, making them highly susceptible to erosion. It was during these many periods over about a 5 million year span that the sediment was transported down the main channel and the distributary channels building the fan. The last time active deposition occurred was about 12,000 years ago. In the future, when sea levels are low again, the canyon will enlarge through erosion and also be the conduit for much transport of sediment out onto the fan. This is all very interesting, but what does it have to do with a line that's over 400 miles away? To understand this, we need to go back in time to about 250 million years ago in the Triassic, when the supercontinent Pangaea existed. This was a period of hostile desert environments for much of North America. The sequence of rock layers deposited have a desert red color from oxidized iron staining. Some of these layers include the Chugwater Formation of the Rocky Mountains, the Moenkopi of the Southwest, and the Dockham Group of Texas, shown here in Palo Duro Canyon. Big changes were beginning to happen. Pangaea was starting to break up, and a mighty rift had started to form along this line, which would ultimately lead to the formation of the Atlantic Ocean.
Let's step back and look at some beautiful paleogeography maps. These are made by Ron Blakey, these deep time maps. They're the best out there. Of course, I'm a little biased. I studied under Ron. He's a great geologist. But here we are in the Triassic period about 245 million years ago. And this was before Pangaea had started to break up, at least significantly. So we have Texas here for reference. We have Pennsylvania. We have some mountains coming down through here that form through the Ouachita orogeny. And all through this region is the great desert that I spoke about, where you have the deposition of these red beds, such as the Dockham Group in Texas. Moving forward in time to the Middle Jurassic, about 170 million years ago, we see evidence of good rifting. Pangaea is definitely breaking up. New ocean floor is forming up through here. It's just off this print. Over this way, along here and into the Caribbean. The Yucatan Peninsula is starting to stretch away from Texas, shall we say, and pull down to its future position, meaning there's some extension here. The crust is starting to thin, but the ocean floor hasn't begun to form in this area. As this continues to pull down and form the Gulf of Mexico, seawater comes in and you have restricted flow and salt begins to be deposited. Well, I think it's time to go to the old whiteboard so we can better understand this process of early extension and rifting and eventual formation of the seafloor. Here I've drawn some continental crust. So we're looking cross-sectionally. This could be, thousands of miles across, this huge block of continental crust. We have oceanic crust on either side in this case that I've put little dashes in or vertical lines. And we have the seawater that I've put here. Now, for whatever reason, sometimes upwelling or these big convection cycles from within the mantle come up. And they can go like this, in a direction like this, coming up and across. Big convection cells. Now, it's pretty simple when you think about it. With this convection cell going this way, the movement within the mantle rock going this direction and this direction on this side, well, you're essentially starting to put a lot of tensional stress on this continental crust. You're pulling it apart, and it can't handle that stress, and it starts to break up. Phase 2, the continental crust is beginning to break apart brittly. Now, a point I want to make is this is not to scale. Remember, the continent can be 1,000 miles wide or wider easily, but this zone of deformation where it's getting pulled apart and broken up, it's not that wide, but it is quite wide. It can easily be 200 to 300 miles wide or even wider, I'm sure. At any rate, this continental crust is thinning by faulting, brittle deformation. These big blocks of material are slowly sliding down and rotating as they slide in. And so the land surface is dropping down. Overall, it's dropping down, and eventually you get below sea level. And this is important because it's very common. Here's sea level. Here's the ocean on each side I've done. Now I want you to imagine a big fracture dividing the continent and going lower and lower, and it gets below sea level. It will find the ocean at some point, of course. And then ocean water is allowed to come in through this and form this long, narrow seaway. And of course, the circulation within that long, narrow seaway is very poor. And especially if you're in desert areas with this poor circulation and that hot sun coming in and evaporating seawater, you raise the salinity. Normal seawater is about 3.5% salt within it. But if you have that evaporation occurring and circulation is poor, eventually you can get that saturation up by tenfold or so, and it's super saturated, and salt begins to just precipitate and fall to the seafloor. So using my red marker here, I'm going to start putting in salt along here like this. Precipitating salt. And in the case of the formation of the Gulf of Mexico and that rifting, that salt, it's named the Luan salt, is up to 4,000 feet thick. And that's a lot of salt. And if you want to learn more about what happens to salt in that, watch my other video on the Gulf of Mexico. But here we've precipitated out this salt up to 4,000 feet. That takes a tremendous amount of the evaporation of seawater. I want you to do a thought experiment with me. The room you're sitting in right now watching this, let's imagine for a minute that everything's watertight, the doors, the windows, everything. But we're going to make that ceiling go a lot higher. Let's make this room you're sitting in right now 1,000 feet tall. That's some tall room, isn't it? And we're going to fill it full of water, seawater, with 3.5% salt. If you have it out in the hot desert sun and leave it out there for a very, very long time and evaporate it all down to where there's no water left, how thick might the layer of salt be at the bottom in your room? Well, it turns out it's about 17 feet thick for 1,000 feet of seawater, 17 feet of salt. Well, if you do the math on that, to get 4,000 feet of salt, you need a water column that's 45 miles, you'd have to have the room 45 miles tall. And the only way that happens, of course, is you're continually bringing in new seawater as it evaporates in this highly restricted environment, and eventually you can come up with 4,000 feet of salt. Wow, this is wild to think about. It seems almost impossible, doesn't it? But if you think of deep time, if you take 1,000,000 years and evaporate just 3 inches of seawater in this restricted seaway, 3 inches a year for 1,000,000 years, you can get to 4,000 feet. So then with deep time, it doesn't sound so crazy. Okay, I've sketched the final phase here that I want to discuss here on the whiteboard anyway, where the rifting has continued until it's created the mighty gash in the continent here that goes down so deep that it accesses the molten rock, which of course cools as it comes to the surface, as it's at the surface, and creates this oceanic seafloor. And this spreading ridge right in the middle, which tends to be high like I've kind of depicted it here. Well, here we are 150 million years ago in the late Jurassic. Boy, the Gulf of Mexico has really gotten large now. The Yucatan Peninsula still has a ways to go to the south, but we have a lot of oceanic crust seafloor that has formed, an active spreading ridge. It runs right along here, that ridge did. And the fascinating point is that it was only active about 5 million years, and it formed the seafloor of the Gulf of Mexico, formed the Gulf of Mexico, and then shut down. Now also, this happened to be the maximum extent of the coastline of that ancient Gulf of Mexico, which runs right along here. And that happens to be the line that I show on the map that's so mysterious.
How is it that the ancient Gulf of Mexico shoreline is so far inland from the modern shoreline? In fact, if you measure from the northern ancient shore to Galveston, there is some 300 miles of separation. One might think that the sea level must have dropped a lot to have the shoreline move so far south. However, current sea levels are relatively high, and it isn't the reason why the shoreline has moved. Actually, it is moving ever to the south because the Gulf of Mexico is filling with sediment, and the geologic history of that filling, as well as the future geologic events, are absolutely astounding. Often observations at the small scale help us understand the very large scale. This very small rivulet of water is transporting sound out to a small pool of water adjacent to the larger river. As we can see, it is steadily filling in a miniature bay with sand. Notice the several lobes of sand built out as the mini river moves from side to side. Pretty darn neat. A mini delta.
A cross-sectional view of an ocean basin, such as the Gulf of Mexico basin. Here's the ocean floor going down through out here into the deeper water. Here's sea level. And now about the processes that occur to fill in ocean basins. There are many, but one of the significant ones, one of the big guys, is very common, is the building of deltas out into the ocean, much like we saw in the miniature version earlier. So we have rivers coming to the shore and depositing and building out a delta. And at the very large scales, this is what we see in the geologic record when we look at it using seismic, which I'll get into a little bit later what seismic is. But we see these surfaces, I'll say. So the rivers come out and they start building out a delta. And it's very close to sea level, the top. And it's very flat if you look at the top of a delta. And actually we saw that in the miniature version, didn't we? Right near the top. And then it has the slope that goes down and on out, depositing sediment way on out. Now, if you think about it, as the rivers come in and they drop their coarser grains first, the heavier material, the coarser grain, like sand. So the Mississippi River has sand in it, fine sand. It deposits that sand quickly right out in here as it builds this out. So this area tends to be sandier. And it's not surprising as you go out into deeper water, what you have are shales that are deposited out here in front. The prodelta is what we call it, this region out here.
Here's a wonderful example of the principles I've been talking about in the East China Sea, where you see a lot more sediment being deposited closer to shore, and of course it would be coarser grain, fine sand or silt. Only clay-sized particles make it further out into the ocean, creating this beautiful plume. And as you would expect, the Mississippi River Delta has similar processes at work. This false color image of a small portion of the Mississippi River Delta shows the intricacies and the beauty of the sediment plume.
Well, this continues through time, just time and again, big cycles of it. So let me put in a new layer, very close to sea level here. And another huge deposit, thicker here near shore, this thickness here, and then less out here. Shales and sand. And it continues on, just steadily filling in that ocean basin with the deltaic processes. There's some other processes I'll be discussing here in a bit. Now, this area here continues to build up. It's very close to sea level initially, and then the rivers build out here, and it steadily builds it up until it's actually slightly above sea level. Again, we saw that in that miniature version, didn't we?
There were also periods of time when there were beautiful reefs and associated deposits that dominated the filling of the Gulf of Mexico. Let's learn why and how that happened.
Continuing with this filling in the Gulf of Mexico, I've got another drawing that I've made. The red line here is the ocean floor of the original Gulf of Mexico. And as we've talked about, it's been filled in significantly by, in this case, primarily deltaic systems with the associated sand and mud. And we have sea level right here, and it's continuing to fill out. Now, under the right circumstances, you can have carbonate deposition take over in the form of reefs and associated deposits that build carbonates or limestone within the Gulf and filling it in, and it's significant. So we imagine here the active deposition is occurring the heavy deposition is occurring right near the shoreline and building out a new system. But if we raise sea level, an interesting thing happens. And we're going to raise sea level up to, say, about here. Now the active deposition from the sand and mud coming in from rivers is way back over here, not over here where it was. It moved back, and this can be hundreds of miles back this way. And what that means over here is that the water is clear. And during this period, it was also warm. So you have warm, clear seawaters, and carbonates can start to develop. And that did happen in the Gulf of Mexico for a period. So right here at this break, you can have a reef begin to form, reef deposits. And back behind the reef, you have carbonate deposition as well. So we'll put red here for carbonates. Back behind the reef, landward. And that's called a platform. And these were common for a period of time in filling in the Gulf of Mexico and became quite significant at times.
The closely spaced red and yellow lines show the location of the two major reef trends that were active from about 115 to 105 million years ago. They formed a Great Barrier Reef with a carbonate platform shoreward of the reef, much like modern Belize. Here is a nice image of Belize showing the barrier reef and the platform behind it. Indeed, it must have been a very beautiful place with warm, clear, shallow waters on the platform and deeper waters seaward of the reef. I'm sure you've noticed that the reefs trend along one of the most prominent and distinctive features in the Gulf of Mexico, the West Florida Escarpment, and what a history it has.
I have a friend named Wank who's a real geology lover, and she thought it'd be really neat to create a genuine Wyoming Jurassic Age fossil kit, and she has spent a lot of time out in the hills on private land collecting these wonderful fossils, fossils of ancient oysters, squids, and my favorite, crinoids. Crinoids kind of look like plants. They attach to the seafloor and have a long stem and then a head or like a flower on top. In fact, some people call them sea lilies, but they are animals. And it turns out the stems, the long stems in this case, are star-shaped, and they break up into these wonderful little pieces that are quite neat. She takes these fossils and puts them in some genuine Jurassic Age sand and includes a magnifying lens, some tweezers, and a special surprise, by the way, and puts it all in this nice box. I think it's a great product. Check out her website by going to the link that I've included in the description to this video.
Hi, I'm Wink. I hope that this kit will inspire you to look deeper into our Earth's history.
I'll bet most of you, if not all of you, know right where I am. Indeed, I'm up the edge of the Grand Canyon. What an amazing place. I've been here many times, and each time I come here, I'm surprised at how huge it is, both in size and scope and depth. And I know you're confused as to, well, what does this have to do with the Gulf Coast or the Gulf of Mexico? And I'm a big believer in trying to communicate scale when I teach geology. And in this case, I thought it'd be appropriate to use the Grand Canyon to help us understand the scale of that Florida escarpment. Now it turns out to hike down to the bottom of this canyon here takes about 5 to 6 hours, and it's about a 5,000 foot drop. It's a fairly gentle slope. That's a pretty big hike. That's a long ways down there. But now let's take an imaginary trip that's similar. We're going to go and drain all the water out of the Gulf of Mexico so we can do this imaginary trip. And we're going to stand on the top of the Florida Escarpment and take a look and start hiking. The first thing we notice from above is we have a fairly gentle slope, a little more gentle on average than here. The river's 2.5, 3 miles out there. It's on average not super steep. Same with the Florida Escarpment. It's actually not as steep as this. And we'd look at that and we go, we can hike down that. Let's go down and hike to the bottom. So we start our hike. We get about halfway down or so and we start to see out there and we think, is the seafloor that we've drained the water out of in this imaginary world, it seems to be further down. And we get further. And we become more and more confident that we have missed something. And the seafloor is much further down than we thought. And we hike our full 5 to 6 hours, just like here, 5,000 feet. And it's clear that the seafloor is way beyond us, down beyond us. And for that to happen, there has to be a big cliff. And it's going to be a bit exciting, isn't it? So we hike over and look off that cliff. It's nearly vertical. that 60 plus degrees in many places, vertical, and it goes another 5,000 feet. That's 2 Grand Canyons. We hiked down a more gentle part of it, and then a vertical cliff for the second Grand Canyon. When we think of that, and plus we think on the Florida Escarpment that it carries for hundreds of miles, and compare it to this Grand Canyon, well, that's pretty darn amazing.
The size of the Florida Escarpment is astounding, but the history behind its formation is equally, if not more amazing. Direct observations along the face of this great cliff, in addition to information from seismic and wells drilled, inform us that it is composed of carbonate reefs and associated deposits.
My sketch of the Florida Escarpment. Of course, the steep portion that I've been talking about is right here. This is like 5,000 feet, 1 Grand Canyon that I've mentioned, and then a more sloping part here, another 5,000 feet. So the total height above the seafloor is some 10,000 feet or even a little more. Of course, this represents the ocean, the sea level here. Florida would be off to the right, even a little further here. So we have a platform area back here, what we refer to as a carbonate platform. And we can see that there's been some fill of sediment up against this escarpment down here low. And remember, the water depth out here off the side of the escarpment out here is some 10,000 plus feet of water. I've mentioned these reef deposits that make up the front face of this, especially of the escarpment. And I've drawn that schematically by all these little humps or hill-looking things. Those are these reefs that have built up. And think about this. This is amazing. We started down here about 160 million years ago, the oldest reef, and it just kept building and building, one after another, on top of each other, moving around a little, just building this zone of reefs. And it just kept going through time up till the very top here is about 23 million years ago. And then they died out. For reference, the water depth out here on this front edge is usually around 1,000 feet or so. This, of course, is depicting the modern day sea level. And you think about this long history, stable history of just reef after reef after reef. And at first you might think fairly simply about, well, that's pretty neat to imagine and think about back in time that I had a reef here and then here and build and build and build. But if you think a little more carefully, there's actually kind of a problem here. Because where do we find reefs today? That's the question I have for you. And I know if you've had the opportunity to be out around reefs, you know they're right at sea level where those waves are crashing. They're dangerous to ships and boating, etc. They're right at sea level. So what that means is this first reef here, sea level, was right here. Oh, wait a minute. Today's sea level's here. This is, well, to the sea floor is 10,000 feet. These are even a little further down. We'll say 13,000 feet. You mean to tell me sea level was 13,000 feet lower than it is today? You see, when geologists see something like this, they start thinking in that way. They think, sea level 13,000, because it had to be here. It had to be here. That's where reefs form. And not only that, sea level had to keep rising and rising, and these reefs just building right along with sea level, always in that optimal zone. They were healthy reefs for a long period and just kept on building right to here. Now this is a real issue because in fact the data, when you study the data, and geologists have done a lot of this, the sea level at the time these reefs were built, you know where it was? If you look at the absolute sea level, is 400 feet higher on average, sometimes quite a bit higher, than where it is today. And if you think of it that way, what you're going in your mind, you're saying, So that means this reef was way, way underwater because the sea level was higher than it is today. So that's a real fun thing to think about, isn't it? You start thinking about, well, maybe reefs behaved differently back then. Were they different animals? You run through all this. Now, it turns out for geologists, this is fairly easy to figure out because they've been exposed to these types of concepts and situations a lot. But for a person that's not familiar with this, it can be kind of puzzling. So I think now you can see how geology often, when you make geologic observations, it often introduces new puzzles and new fun things to think about, and this is certainly one of them. And in this case, the explanation of how you have this relationship ties back to a concept called relative sea level. The absolute sea level that I mentioned to you, that's about 400 feet higher back during this time than it is today, that's what we would refer to as absolute sea level. But there's this principle of relative sea level. I want you to imagine for a minute that you're standing right here on this point and sea level's lower, it's right at your feet and the waves at your feet. And actually you go out there every day and you start to notice that the water is getting deeper and deeper and deeper. Sea level is rising. It's relative sea level low because you're not sure. You don't know if the sea level is rising or if the ground is subsiding. And that's the key to this whole mystery. Sea level wasn't rising. In fact, sea level was dropping through time to the present day. And that means that the ground, the seafloor, this whole region was subsiding through time. And if we think of it that way, that using relative sea level, that means that this reef, with the sea level at that first reef, in true space, and absolute sea level space was up here, probably about 400 feet or so above the sea level today. And that everything subsided through time. And the sea level, relative sea level was rising, but the reefs were keeping right up with it, growing as fast as they could go, keeping right up with sea level. It turns out that reefs just don't drown. They can keep up with a relative rise in sea level, the water getting deeper and deeper easily. They just grow right, one animal on top of another, and build up and keep up through time with that change in sea level. No problem. Now about this subsidence. So thinking about this relative sea level and that this reef was way up here and now is way deep, that means it subsided through time, the whole landmass, as I've mentioned, a lot, some 13,000 feet or so. And the way that happened involves three things. One is the opening of the Gulf of Mexico. You're pulling in a hole, things are dropping down. That's some of the subsidence. Then another thing that's occurring is once the Gulf is opened and all that heat involved in the rifting and everything stops, and the rifting stops, then things start to cool. And so you have thermal subsidence. So that accounts for some of it. And the last thing, which isn't insignificant, is you load all this material, building all these reefs and all this sediment being deposited in the Gulf, it depresses the lithosphere down into the mantle some. It depresses it down and loads it. Isostatic loading. And that depresses it further, which means even more subsidence. So you add all those together, and through time, you had that 13,000 feet or so of subsidence. Pretty amazing to think about.
With our understanding of the escarpment, let's look at some seismic images of the Earth. This image is a cross-sectional view that starts from the escarpment on the right and crosses into the deep waters of the Gulf and is about 65 miles long. I've colored the water blue. These images are created by sending acoustic energy into the Earth and then recording the sounds that reflect off of the Earth's layers, and then doing some serious computing to create the image. It's like a sonogram of the Earth. The faint lines you can see are the thick layers of sediment or rock. The pink color you see is something that I added, which shows where the salt is. Notice this bright reflector deep in the Earth. I've highlighted it here. This was the bottom of the ocean about 65 million years ago at the end of the Cretaceous. Boy, there has been a lot of sediment infill on top of that since then. Here is another line going from the very dramatic escarpment on the right westward out into the deep water to the left side of the line. It's about 250 miles long. The same top of Cretaceous marker is seen here. This line has additional interest because it shows deposits of the Mississippi Submarine Fan that I've highlighted. I've marked with a blue line the total amount of sediment that is filled in on top of the oceanic crust. The water depth here is about 9,500 feet, so it's a ways out there in the Gulf. A fun question for you. How many feet of sediment do you think this is? I'll give you 2 clues. Number 1, you can't use the height of the escarpment and use it for a scale. It turns out seismic is measured in time, the time it takes for the acoustic waves to go down to a layer and back. With a lot of work, this time can be converted to depth, but it would look different. It would be stretched a bit. The second clue is that it is likely more than you can imagine. In fact, it's about 30,000 feet. That's nearly 6 miles. And another interesting point is most of it has been deposited in the last 65 million years. Now, where on earth did all that sediment come from?
I'm on the banks of the Bighorn River here near Grable, Wyoming in the Bighorn Basin. And it's the major river that drains all the material that's being eroded out of the basin outwards. This river drains 2 major basins here in Wyoming, and in fact they're big basins for the entire Rocky Mountain region. And it has removed a lot of sediment. These basins used to have lots of sediment within them that has been eroded, formations that were deposited millions of years prior. And we're going to learn just how much by taking a drive up a mountain in the basin here to see that.
As I drive along, I ponder the amazing history of the Gulf region and its connection to the Rocky Mountains. In particular, it amazes me to think of all the material eroded from just this one basin that was carried out into the Gulf of Mexico. I'm well above the river now, and believe it or not, the sediment fill at one time was higher than this. As the great mountains that surround this basin were uplifted about 65 million years ago, a huge amount of material was eroded off the tops and deposited into the adjacent basin, slowly filling it up. The mountains seen here in the far distance across the basin had similar amounts of material eroded from their tops.
What a place, and what a drive. That's a fun drive coming up to the top of this mountain. We've come up 1,000 feet now above the river. And of course you're wondering, did the sediment level, the fill of this basin, come to this 1,000-foot level? That's an awful lot to fill that 120 miles by 80 miles. Wow, well, it did. It did come to here. And now we can start to think of this is a tremendous amount of sediment that is washed out into the Gulf. Whew. But you know what? I'm holding back on you. It turns out it came up to much higher than this spot. In fact, the sediment level came up to right at 5,000 feet over my head, to an elevation of 10,000 feet. That's the top of the Bighorn Mountains right here, right at the top, right here. Only the highest peaks were shown above. Now with this information, we can really start to understand that this is a huge volume of sediment that is eroded out and gone into the Gulf of Mexico. Crazy to think about.
But just when you begin to understand the scale of the processes involved, you learn new information that takes it all to another level. We started this journey learning about the Mississippi Submarine Fan. Question: do you think all the sediment removed from the Bighorn Basin is enough to create the fan? After all, it is a relatively recent development and accounts for a very small portion of the fill way out in the deep waters, as shown on this seismic line colored in red. Well, it turns out that it would take over 7 Bighorn basins filled to the brim to create the fan. I'm accustomed to studying very large geologic features, and even for me, this is hard to get my head around. Now for the grand finale. We'll do this by looking at a geologic cross-section that runs along the white line.
We've seen some amazing geologic features and at very large scales, really hard to comprehend. And when you put it all together, it's even more incomprehensible. And I hope this cross-section will help you think that way. So to orient ourselves, on the right over here would be Mexico, the Yucatan Peninsula. It has an escarpment that's very similar to Florida. And of course, this would all be limestone and reefal material. On this side, over here, would be the Texas-Oklahoma border. So that's some 900 miles across. The heavy red line is the original seafloor of the Gulf of Mexico when it opened up. And of course, everything on top of that line is the fill sequence. And sea level, of course, is here, the blue line here, and this arrow here is the coastline today in Texas. This cross-section goes through Texas, so that is the actual coastline. The water's pretty shallow here for a ways. Now, I've divided the fill into 2 major sequences. The first one here goes from about 160 million years ago at the start to 65 million years ago. And this sequence here is everything younger than 65 million years. And then, of course, all this is ocean water here. I've tried to make this sketch fairly accurate on the vertical scale, the depth scale, so the proportions should be pretty good. The horizontal scale should be reasonably good. But we look here, and this lower sequence, if we look at it, it's about 15,000 feet thick right here. Remember, this is 10,000 feet of water. We remember that the early deposits on top of this surface, at least over here and up in here, they were salt. Those deposits were salt. And then dominated by a lot of siliciclastics, or muds and sands. And over on the carbonate shelves of the Yucatan Peninsula here, we do have limestone deposition, a platform that continued through this whole period, as well as the Florida Escarpment. And I'll point out where the reefs that we discussed about earlier in the video, the ones that run along the Gulf Coast, they reside about in this area. That's 15,000 feet underground. Now for the next sequence, the 65 million years and younger. An interesting thing about this sequence, there are no reefs in it, except for on the Yucatan Escarpment. There were reefs growing during this period in the upper part, as well as the Florida Escarpment. But everywhere else, reefs were none to be found. Carbonate deposition was shut down. Thinking about that, what kills reefs? Muddy water. There must have been a huge influx of muddy water to kill off all these reefs. If you think about it, 65 million years ago, that's the uplift of the Rocky Mountains and the formation of the Mississippi River. So the muddy Mississippi, wow, it brought in all that muddy water and made the environment just not a good place for reefs. I think it's really neat that you can look at the sediments in the Gulf of Mexico and tie them back to the uplift of the Rocky Mountains. Man, geology can really get interesting. By the way, I'm sure some of you have been trying to figure out about how thick this overall package is of fill, where it's the maximum fill thickness. It's 45,000 feet plus. A comment about deep water sedimentation. We started that out by talking about the submarine fan, the Mississippi Submarine Fan, way out in deep water that goes clear up to the Yucatan Peninsula. I mean, it would be very small on this scale. But all this sedimentation out on this side was in deep water through time. There are 2 main processes responsible for this sedimentation out here. The first would be the organized submarine fans that we've discussed. The second would be turbidites that come out from the shelf. They're like snow avalanches. They're avalanches that come off the shelf, this muddy water that has high density, and it just avalanches down, and it can run way, way out across the basin. Wow. With this picture, you start to, it just blows your mind to think about everything that has occurred in this region and the scale of it all. And this relatively small space that's left to fill. It seems huge today. The Gulf of Mexico, wow, that's big. 10,000 feet of water. You see it at this scale, it makes you start to think, doesn't it? I think we've reached a time now that we need to flip geology and talk about the future using geologic principles. We can see the writing on the wall. The Gulf of Mexico is going to fill full of sediment. Yes, entirely full, right up to the brim. It will create a broad, flat coastal plain, much like the Gulf Coast is now. And of course you're wondering, right along with me, well, when is that going to happen? When will that completely fill? And I think with the information that we've covered, you can make as good a guess as me. So have fun thinking about that. I've had fun making this video. Would you consider subscribing by clicking on that small round photo of me? Thank you for watching.